Now let's consider another situation. Suppose we wanted to find an inverse of the function f of x equals x squared. That's a simple enough looking function. It wouldn't seem problematic to find an inverse for x squared. Consider a table of solutions for this function. So we just see some x's, and then the function values are the squares of the x's. So negative 2 squared is 4, negative 1 squared is 1, and so on. Now we know that if the inverse of f exists, it must reverse the action of f, so that the inverse would therefore have to include the following solutions. So we see for the original table, negative 2 for x is associated with y equals 4. So for the inverse, that pairing should be reversed, and now x is 4 and y is negative 2. Similarly, we see that negative 1, 1 in the first table corresponds to 1, negative 1 in the second table. We know this must be the case because the inverse of a function must reverse the action of the original function. The problem, however, is that when we reverse the x's and y's for this particular function, we no longer have a function. If you look at the second table, let's just take as an example 4, negative 2, and 4, 2. Okay, these correspond to reversals of negative 2, 4 and 2, 4 from the table for f of x equals x squared above. But when we have an x that corresponds to more than one value of y, as 4 does in the second table, we no longer have a function. The same thing happens, notice, with 1, x equal to 1. 1 gets associated both with negative 1 and with positive 1. Again, we can't have that occur if we have a function. Every x should be associated with 1 and only one y value. So the problem has to do with the fact that for different x's in the original function, different x's are getting associated with the same y value. So if we want to be able to define an inverse function for a given function, this kind of thing cannot occur. Every x has to be associated with a different value of y. There cannot be any repetitions of y values for different x values. So for a function to possess an inverse, we insist that the function be one-to-one. So just reading again below the second table. This problem occurs due to the fact that for the function f, different values of x are associated with the same value of y, as I pointed out with negative 2 and 2, both being associated with y equals 4. So for a function to possess an inverse, we insist that the function be one-to-one. And then we see the definition of a one-to-one function. A function f is said to be one-to-one if for any values x1 and x2 in the domain of f such that x1 and x2 are not equal, are different, the function values have to be different as well. F of x1 cannot equal f of x2. In other words, different x's always correspond to different y values. If that doesn't occur, then the function will not be one-to-one, and it will be impossible to define an inverse function for that given function. We might be able to define a relation, but it will not be a function. It turns out that if we can graph a function, it's very easy to determine whether or not it is one-to-one. So there's a graphical test for one-to-one functions. And you may recall from the very first section we covered, section 2.4, we mentioned the vertical line test for functions. The vertical line test is used to determine whether the graph is that of a function or not. For one-to-one functions, we have a similar test called the horizontal line test. The horizontal line test for one-to-one functions. It says that a horizontal line will intersect the graph of a one-to-one function at most once. For example, the graph of f of x equals 2x minus 4 passes the horizontal line test. Any horizontal line that you draw through the xy plane will intersect that line at most once. What that means is that for that particular y value, there is only one x value that gets associated with that y value. Notice for all the different x values, we always get different y values. There are no repetitions of y values for different values of x. So if a function is one-to-one, we can check and see that its graph will pass the horizontal line test. On the other hand, the graph of f of x equals x squared, which is the example we were discussing just a moment ago, does not pass the horizontal line test. If you look at x equals 2 and x equals negative 2, these are the values we were looking at a few minutes ago. The points associated with those values of x both share the same y value. And if we draw a horizontal line through those points, we see that it intersects the graph more than once. So clearly that's not a one-to-one function based on the horizontal line test. So it's pretty easy, if you can produce a graph of a function, to determine whether or not it is one-to-one by applying this horizontal line test. Now, for f of x equals x squared, although over its entire domain, which is the set of all real numbers minus infinity to infinity, over its entire domain, it's not one-to-one and therefore does not have an inverse. It is possible to restrict the domain in such a way that we produce a one-to-one function, as I will demonstrate next. Notice if we go to the next page, it says if the domain of f of x equals x squared is restricted to the interval 0 to infinity, the function is one-to-one and has an inverse. And its inverse is what you would expect it to be. You want a function that reverses f of x equals x squared, or cancels it out, so to speak. It would seem reasonable that the square root function would serve that purpose. So its inverse is the square root function if we only use values of x that are non-negative, from 0 to infinity. Graphically, what that means is we're only looking at half of the parabola from the origin to the right. So we're just looking at that right-hand branch of the parabola. And if we only consider the right-hand side of the parabola, the graph will pass the horizontal line test, and therefore the function will be one-to-one. Notice that in doing this, we don't lose any of the y values that we get for this function. We retain the entire range of the function, which is also non-negative real numbers from 0 to infinity. So usually when we restrict the domain of a non-one-to-one function to produce a one-to-one function, we want to do so in such a way that we do not restrict the original range of that function. This is actually very commonly required in defining inverse functions. A lot of times we have to take a given function and restrict its domain in such a way that it will produce a one-to-one function without losing any of the range of the original function, just as I've demonstrated here with f of x equals x squared. Now, how might we find the inverse of a one-to-one function if we don't know what it is? It's not given to us in the problem, basically. For many functions, there's an algebraic approach that can be used. It can be essentially boiled down to a four-step process. It's not always possible to apply this process, but very often it can be used. So to find the inverse of a one-to-one function, step one would be replace f of x with y, then interchange x and y within the equation, solve the new equation for y, and then introduce the notation f inverse of x, replacing y with that notation. You may recall in a previous example, we showed that we had f of x equals 2x minus 4, and we had g of x equal to x plus 4 over 2. And we showed that those functions were inverses using function composition. Let's apply this four-step process to example 2 and actually find the inverse of f of x equals 2x minus 4, this function here that we looked at earlier in an earlier example. Let's apply this four-step process to actually find the inverse directly from f. So this is a one-to-one function. We actually looked at the graph of this function. It's a straight line, so it is a one-to-one function. So we can find its inverse. And so we go through this four-step process, and I'll just number them as I do it, for f of x equals 2x minus 4. First, replace f of x with y. So write y equals 2x minus 4. Step 2, interchange x and y, or swap x and y. So for where you see y, write x. Where you see x, write y. Solve the resulting equation for y. So I'm going to put 2y now on the left, and I'd have to add 4 to both sides. So that would give me x plus 4 on the right. I've just switched sides with the variables, if you don't mind. And then we're still in step 3, solve for y. Y equals x plus 4 over 2. And then as our final step, use the new notation, f inverse of x, to represent this function. This is the inverse of f of x equals 2x minus 4. As you can see, that's identical to the function we were pairing with f, the function we called g previously from the earlier example that we did. I guess that was example 1. Since this is just example 2, I couldn't remember the example. It must have been example 1, of course. Okay, so it's an easy method to apply, assuming it's possible to solve the equation algebraically for y, and sometimes it's not possible to do. So we can't use it with every function, but for some functions we can use this four-step method to find the inverse. We're going to do another example, example 3, working through this same process. We'll do that in the next video.